Thank you. Thank you guys for having me. I hope you guys are having a good FOSDEM. My name is Mohammed Osama, and I'll be presenting Gunrock, which is our graph processing library built on GPUs using CUDA. I'm a PhD student at University of California working with Professor John Owens, and I flew more than, I think, 14 hours to give this talk, so let's hope it goes well. So this is a link to the talk. If you guys are interested in downloading it and following along, I'll give you a second to take a picture or something. All right. So just a second. So why use GPUs for graph processing? I didn't feel the need to actually sort of give a motivation of why graphs are important, because obviously you guys are in this dev room, so maybe you care about graphs. But how can you use GPUs to sort of do graph processing better or faster? And how did we manage to do it? Well, so graphs are everywhere. GPUs are nowadays everywhere as well. Your phones, your laptops, everything now has a GPU in it. Graphs require fast processing. It's need within the memory and the compute that you'd require to do some graph analytics. GPUs sort of give that powerful memory bandwidth and computation together. So it goes really well hand in hand. Graphs are becoming very, very large. There's billions and billions of edges in graphs nowadays within Facebook and Twitter. Yeah, there's a need to process a really large data sets. GPUs, however, are not good at that. We have a very limited amount of memory. 32 gigabyte, I think, is the most in an NVIDIA V100. And I'll talk about how we handle some of those issues. There's some irregular data access patterns within graphs, which makes load balancing quite hard and a really difficult problem to solve. So writing high-performance graph analytics and graph algorithms really require you to get load balancing right. And that's really hard to do on GPUs using CUDA. So we show a way to solve that as well. So what is Gunrock? Gunrock is a GPU-based graph processing library, like I already said, which aims for performance. You can write state-of-the-art graph algorithms using our library. It also aims for generality, so it covers a broad range of graph algorithms, and I'll give you a list of algorithms that we have already implemented and ways that you can implement your own graph algorithm, so problems that you're interested in. So programmability, which is really cool because you can implement your own graph algorithms and then extend it to go from a single GPU to a multi-GPU environment pretty easily using Gunrock. Scalability. So once again, one of the problems was how much memory you have available within a GPU is super limited, but the graphs are really large, so there has to be a way to sort of scale that and still see the performance that you'd need from a GPU. To sort of start off, where can you find Gunrock? Gunrock is hosted on GitHub for, I think, over 3 years now. It's an open source project, has a lot of commits, a lot of contributors, and really active, and a lot of graduate students that work on it too. So this is the link right here to the Gunrock's website, where we have our docs and link to the GitHub page and all that stuff. Some of the open source sort of project workflow stuff. We manage 2 branches on the main repository, the master branch and the dev branch. Master branch is where all the releases happen. The dev branch is where we push all our development work. A lot of it is done within forks of individual people, individual graduate students. And then it eventually gets merged into dev branch, and which eventually sort of trickles up to a release in the master branch. It's hosted using Apache 2.0 license. We also provide code coverage using CodeCov.io, central integration using Jenkins, and lots of documentation using Slate documentation for API, and Doxygen also for API. And some of the performance results and stuff are hosted on Slate, so you can check that out as well. We have unit testing using Google Test, which is really cool. And if you're interested in, or you have any questions, please post a GitHub issue, or if you want to contribute, create a pull request. There's someone there will be someone that will review it or give you feedback on it, and will be able to respond really quickly on that as well using GitHub. We prefer GitHub over emails. So everything related to Gunrock is open source and online. There's no hidden development at all. Even our roadmap is online, so you can go and check that out if you're interested in seeing what kind of research problems that we're trying to solve in future or working on right now, or the kind of graph algorithms that we aim to write, and some of the interesting Hive stuff as well is all on there. Yeah, so I talked about a lot of contributors, bunch of commits, and Gunrock is also part of the NVIDIA GPU accelerated libraries, and also it's being worked into being integrated into the NVIDIA Rapids framework, which is a Python framework that allows you to do data science and stuff. So underneath the hood, it will use Gunrock and some other graph frameworks provided by NVIDIA. So let's actually see how everything works. I heard some people hint towards sort of different graph programming models that exist and graph abstractions that you can use. Gunrock relies on the data-centric abstraction. So vertex-centric abstraction is another name for it. And it uses bulk synchronous programming models. So what does those two words actually mean? So when I say data-centric, we have a notion of a frontier, where a frontier is just a group of vertices or edges. So if you have your entire graph, you just create a frontier using a subset of those nodes, or maybe an entire graph gets put into a frontier. And then you process your whatever algorithm you're trying to write on this frontier. You don't have the notion of the entire graph anymore. So everything works on a frontier moving forward. You have parallel operators. This is what you use to actually do work on that frontier. We have some of our parallel operators, but you're free to write your own as well. These are really high-performant CUDA implementations. This is where all the engineering goes into. So some of the examples I have on the left side are advanced, filter for intersection, neighborhood use, and a lot more. So an example would be advanced, where advanced will take a frontier, an input frontier, and then it will generate a new frontier by visiting all the neighbors. So in the action of visiting the neighbors, you have access to all of the neighbors of a given node or something. And then you can perform all sorts of different operations on that node. And I'll give an example, a concrete example of where advanced is used. Filter, as the name suggests, it just filters stuff out. So you have an input frontier, and you use some condition to filter some vertices out, and you have a resulting frontier that's smaller than maybe the input frontier that you put in. And a lot of documentation is available for all the other operators that there are. And there's some that I don't mention here as well. So what is the bulk synchronous programming side of things? So the operators in themselves are highly parallel, and they run on GPU. And how you write algorithms is you couple these operators together in sort of a bulk synchronous way. So this is one operator. You might have another one after that, and another one after that, and so on. And then you run this in a serial loop. So you perform this in a serial loop. So after every operator runs, there's a synchronization call. And that synchronizes the entire data flow and sort of makes that knowledge available to every processing unit, or whatever you want to call a CUDA core, too. And then all of this runs in a serial loop until your algorithm converges. So these are the kind of algorithms that we currently support. There's some that are being worked on, and so we have some of the traditional algorithms like connected component, breadth first search, PageRank is somewhere in there too. SSSP is there to single source shortest path. And we also have some of more complicated applications which require other algorithms to work. So graph trend filtering is one of them, which requires maxflow as one of its components to really perform the whole application. Another one is shared nearest neighbor, which is a clustering algorithm that requires k nearest neighbors, which is somewhere in here, for it to work. So there's some really concrete real-world examples and some textbook algorithms that you can use to couple those together, or you can couple different operators together to write your own graph algorithm, all working in parallel on the GPU. I also have an example application. I tried to sort of simplify this code as much as I could, but I'll go and quickly explain what each of those lines means. So the first step to implement any algorithm in Gunrock will be to actually implement the lambda functions of the operator that you're going to write. So what lambdas, see these are C++ lambdas. The entire library is written in C++ and CUDA. So what lambdas allow you to do is have the generality of like doing anything within a function. So it's basically a user-defined function. Say you wanted to do a traditional or advanced operator in Gunrock, but you also wanted to attach some sort of notion to it, some sort of like computation attached to it. In this example, in a single source shortest path, the algorithm is quite simple. You have a single source and you want to find the shortest path to all the other nodes in the graph. So you queue a frontier with that single node, and then you basically do an advance. So that's why you need the advance operator. You visit its neighbors, and then you visit the neighbors' neighbors, and you build this frontier of neighbors and neighbors and neighbors over multiple iterations. And then you calculate the shortest distance to that node given a source node. So you take the distance of the source node, that's the first line. So auto distance equals distance of the vertex ID, the source that you're working on, plus the weight of the edge ID, so the weight on the edge, going to a neighbor, or going to a neighbor. And then you find the minimum between that and the existing distance that was in the source node, and if it is the minimum, the predecessor is set to the neighbor node, and you move on. If a shortest distance is found, you'll need some way of removing that vertex from the frontier. Otherwise, the algorithm won't terminate because the frontier is completely full, and you keep doing it, so it will be an infinite loop. So you need some way of removing nodes that are already found their shortest neighbors. So that's what a filter lambda does. It's basically saying if it's still valid, keep it in the frontier. Otherwise, remove it from the frontier. So lambdas are a great abstraction to basically allow users to write their own computation within this. And you can imagine using the same operators with different lambdas to implement a different algorithm entirely. One of the recent ones that I did was graph coloring, where I used for lambda, or you can even use a filter for that. And graph coloring requires is basically a problem where you want to color different nodes with different colors if they share an edge. And you can write that all within a filter operator, but with a different lambda. And all of those examples are online for you to see. So once you have written the lambdas down, once you have actually expressed your algorithm, you launch it. And this is just a while loop while the frontier is not empty. Keep running the advance operator with the advance operator lambda and the filter operator lambda. So you provide the lambdas and you keep running it until the algorithm converges, until the frontier is empty. And that's basically all I have. These are some of the grants that we have that allow us to do this amazing research, and I thank you guys for listening. Left a lot of time for questions, I think. Okay.
Thanks.
Thank you.
There's some time for questions. Anyone?
Yes.
Do you have any benchmark? Will you use this?
Yeah. So on the web. So the question was, do we have any benchmark where we compare our results to other stuff that's being done? Yes, we have online. We have a web page of evaluation where we compare against different graph frameworks and on some of the famous data sets. And one of the recent performance evaluation that I've performed runs over 74 different data sets, which includes anywhere from like the Twitter data sets, social networks, road networks, some of the structured data sets, the RGG, the randomly generated graphs. So anything you can imagine in sort of the graph analytics world, we have a data set for that and a test for that. Yeah. Yeah. Yes.
How do you load a graph, or what
so that's a good question. So we use okay. How do we load the graph? So we take matrix market format as an input. And then we have underlying graph representations, which are the common ones like CSR, compressed sparse row, CSC, which is compressed sparse column, coordinate format, COO. And we also have a graph representation, which you can plug your own graph representation in and then define that under our graph data structure, and will be good to use that going forward. Yeah, so currently we support 3. And there's some work being done by Rapids folk at NVIDIA to support the Apache Arrow format within Gunrock and within their framework as well.
More questions? Yes.
You've mentioned about the frontier, and I'm wondering whether you use any approximation in this algorithm or is an exact.
So the frontier itself, when it's built, it's exact. So you know what you put into the frontier to start off with. But when you do operations like advance, there's policies that lets you determine is it an approximate deduplication or a complete deduplication, where you remove any duplicate neighbors that you found in parallel, or you might want to keep them for certain algorithms where it doesn't matter, which will perform much faster because you don't have to do a synchronization and a deduplication of some sort. So there's support for both. So you can do approximate frontier handling or something, or you could go aggressive and do exact. Yes.
Have you found any functions for which the GPU is slower than the CPU?
One of the ones is actually MaxFlow. So graph trend filtering uses MaxFlow, and MaxFlow, we found that there's a CPU algorithm that just maps so much better, and it's not transferable to a GPU environment. It's not parallelizable. So the one we use, I think, is the Edmonds Carp or push relabel MaxFlow, and it just doesn't do as well as we'd want it to be. But there's a student working on some research and developing a MaxFlow algorithm for that. But that's one example that comes to mind. Yeah. Yes.
The graphics card vendors are likely to address the low quantity of GPU RAM on cards, because it's like you have to buy the best product on the market to even get 32 gigabytes.
Right. So the question is about low memory availability within GPUs, and you obviously need like a high-end V100 to get the maximum 32 gigs. So what we also have is support for unified virtual memory, which is a CUDA UVM driver that allows you to manage memory through CPU by page faulting. So your graph will essentially, you'll load as much as you can on the GPU, and the rest of it is page faulted as needed. But you can imagine that will have a huge performance penalty depending on how many page faults there are and how you're doing them. There's also a multi-GPU environment, so you could buy maybe cheap cards and use the multi-GPU aspect of Gunrock, which is sort of hidden away from the user, which allows you to do the same algorithm in a multi-GPU environment with now more memory available. But obviously, you'll have to spend money on buying more GPUs for that.
I have a question.
Yes.
You showed the SSSP example, and you used these the input values for the lambda to store the result distances and the weights.
Yes.
What are the constraints on those data structures? Can I basically pick a generic value, or is it only a long, or what is
So that can be anything. That can be literally anything. So C++ lambda allows you to capture any of the variables that you'd like. So that those square brackets are the actual capture, where you can capture the data you're working with. So if it's an array, it can be a float or double or int or whatever. And it's all, the entire Gunrock library is templated. So it supports any of the data types that you'd like or you'd want to do. I forgot to mention the sort of parentheses there with the dot, dot, dot. It's, I sort of simplified that for the slide, but it's the signature of the lambda that stays the same no matter what. So it's basically copy-pasted from the API, which provides you access to the vertex ID and the edge ID, because that's how you get those. Yeah. Yes.
Any more questions?
What about graph embeddings? I saw that you have graph stage on it. Can you say a little bit about that?
So I'm not the person that's working on graph embeddings, but you can have any sort of data struct or struct attached to node labels or edge labels, and then you pass it in the same way and capture it within the Lambda, and you should be able to work on it. That's my 20 minutes.
Okay, let's thank the speaker.